Good day, folks. Today I'd like to do a step-by-step with you for building a type of Don Smith. Basically, his latest project around right at the time before he died, where he had a portable setup and he claimed that it would look nothing like what people are used to in reference to his old devices on how far he developed it. And he never really wanted to give really good descriptions of it, but putting the pieces together, I've been able to. I'm pretty sure I found the interaction, and for some testing I did here with initial prototype, it works pretty well. So basically, I don't want to read the introduction part of my PDF, but I recommend that you all download it. It's a link, and that you follow along because I'm going to be reading in the book. So this is going to be a long video. So I warn you right now, you'll probably want to pause a few moments and take a breather. I know I probably will myself. And with that said, I'd like to get into the book, but again, I'm not going to read the description. You can if you want, because it's essentially what I'm saying here right now to you guys in the opening. So what I want to say essentially is, before we get into this, folks, I urge you all to not just skip to the circuit diagram and try and analyze it and say it's not going to work, or try and build it without understanding what's going on, because I can tell you right now, you're most likely going to fail. And the same thing as Benini says, you know, you want to modify it, great, but if you're going to do that, make absolutely sure you know what you're doing and the concepts are well understood, so you don't go back at me after and said, oh geez, I built this, but it requires a better blah blah blah, because you know magnetic fields work this way, so I did blah blah blah. Your system doesn't work, how come? So again, you want to modify it, do so, but at your own risk of understanding what it may not work the way it's supposed to work. So again, I urge you to either go through the PDF file on your own or follow along here with me. I actually tried to take great lengths to go back to the basics with this. So everything that I cover in this booklet is absolutely necessary to understand. So it may look tedious essentially when it gets into the first thing, what is a capacitor? But the description, folks, everything, every word in this booklet is fine-tuned in a way that you can understand what this is getting at. It's all in reference to what we're doing. So there is a whole point that it's getting at, but you got to build it up, and we want people to be able to understand. You see, Don Smith gave you these hints, and most of the time they were basically deceptions. I don't want to do that, and for the reasons that I noted in the description, my plan is not just to go on YouTube and show off a working devices and, you know, get famous off of that and little contribution. Everyone can, you know, plus what happens with that, you get high profile, it's not good, you're on the radar, and I don't make any money with this, I don't need the drama. Again, I explain it all in the beginning of the booklet, and it's well reasoned, and I'm really reasonable too. So I decided, you know what, based on my own previous experiences posting other things near commercial quality power, it never ends well. It gets scrutinized, it gets laughed at, or people want measurements, and then when you give them measurements, they want the measurements off. So you know what? I'll give you the information step by step, the understanding. If you understand this, you'll be able to make this device and variants of it on your own. And you'll be able to succeed and even enhance on it. So this is a starting point to let you folks know what you can do with novel interactions, and when we use devices in unconventional ways to get things done more efficiently. That was part of Bedini's trick. That was also part of Don Smith, but Don Smith was not as straightforward with it. He would show you a homemade capacitor, all right. We all know that could store high voltage and sparks and whatnot, but without getting into great lengths into what exactly he was getting at. So anybody can go on a stage and wave their hands in the air and scream resonance, 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 but again, without any specific details of what you're doing with that resonance, it's a wide scope range of possibilities here. So without further ado, here's the booklet. Understanding and Building the New Don Smith Device by Joel Lagacé. You can download this. I bind it and made it in a book, so it's nice and tidy. So going into the first part, you know, this is my introduction, which I basically said it out loud here. So go into the content, just to give you an idea of what we cover here. How inducers work, ferromagnetic versus pure resonance, such as non-ferromagnetic effects, self-capacitance and traditional coils, Traditional systems and efficiency considerations. What is a capacitor? How capacitors work? What is resonance? Reactive power versus real active power. What Don Smith tried to tell us. Building the new Don Smith device. Of course, device diagram and detailed workings. This is the must read before attempting to build part. Basically, part one here, I'm sorry if this is boring, but I've once just submitted a PDF files and people were like, we don't mind if you read it to us. Okay. I think that AI voices would be better than mine, but hey, if you guys want me to read it and try and explain it again in my own words, I'll do my best to do that. So here we go. How inducers, sorry, it's already on the bad start. How inductors work. Inductors are components in an electrical circuit that stores energy in a magnetic field when electric current flows through them. They are usually made of a coil and a wire. So basics of inductance. When current flows through the wire, a magnetic field is created around it. If the current changes, this changing magnetic field induces a voltage in the coil, opposing the change, known as Lenz's law. We talk a lot about this, so nothing new so far. And the ability of an inductor is to induce this opposing voltage. It's measured in Henry, H, which defines the inductance. Something we already know, but we're putting it out there. So the applications, inductors are used in filters, transformers, and energy storage in electronics. So hint, hint, hint. So there's a reason why we talk about these. So moving on now. Ferromagnetic versus pure resonant non-ferroelectric effects. Ferromagnetic response, core materials. In many inductors, ferromagnetic materials like iron are used as a core to concentrate and enhance the magnetic field. This increases the inductance. So magnetic hysteresis. Ferromagnetic cores exhibit magnetic hysteresis, lag between the magnetization and the applied magnetic field. This adds energy loss as heat and limits high-frequency performances. Applications suitable for low-frequency, high-power applications. Example, transformers and power grids. So pure resonant non-ferromagnetic response. Coreless or air inductors. These are purely on the coil geometry and do not use magnetic materials. Higher frequencies. These inductors work well at high frequencies because there is no core material to introduce hysteresis or saturation effects. Applications used in radio frequency RF, circuits, and high frequency resonance systems. Hint, 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 right? So now moving on to self-capacitance in traditional coils. Yes, there is self-capacitance in the coil. So what is self-capacitance? In a coil, the wires themselves can act like plates of a capacitor. This is due to the proximity and adjustment turns in the coil, allowing a tiny amount of capacitance between them. Implications of self-capacitance. Resonant frequency. The combination of inductance and self-capacitance creates natural resonant frequency. At this frequency, the inductor can act like a capacitor. Limits high-frequency operation. Beyond the resonant frequency, the inductor's behavior degrades, which is critical in high-frequency circuits in traditional electronics. So for traditional systems, designers need to account for self-capacitance in precision circuits, especially in RF and high-speed digital systems. In power systems, the effect is generally neglectable. So traditional systems and efficiency considerations. Energy losses in inductors. Resistive losses due to the resistance of the wire. Core losses from hysteresis and eddy currents from ferromagnetic cores. Radiative losses. At high frequencies, some energy can radiate away. Optimizing inductors. Use high-quality core materials to reduce losses, which we try and do, if that's what we're building, and consider air core designs for high-frequency applications to avoid core saturation. Hint, hint, hint. So moving on, what is a capacitor? A capacitor is a device that stores electrical energy in an electric field. It consists of two conductive plates separated by an insulated material called a dielectric. When voltage is applied across the plates, electric charges accumulate, creating an electric field between them. How a capacitor works. Charge storage. The plates of the capacitor hold opposing charges, positive on one plate and negative on the other. The amount of charge a capacitor can store depends on its capacitance, C, which is measured in farads. So traditional functions of a capacitor. Energy storage. Capacitors can store energy temporarily and release it when needed, like in camera flashes or backup power systems. Filtering and smoothing. Hint, hint, hint. In AC to DC conversion, example power supplies, capacitors smooth out voltage fluctuations by storing and discharging energy. Coupling and decoupling. Capacitors block DC signals while allowing AC signals to pass. Coupling. They stabilize voltage levels by filtering noise. Decoupling. Hint, hint, hint. Timing and oscillations. Capacitors work with resistors or inductors in timing circuits or oscillators, determining how fast a circuit operates. Tuning circuits. In radio receivers and transmitters, capacitors help time to specific frequencies. So the properties of capacitors, we have the different types of dielectrics. Common materials include ceramic, plastic, mica, and air. The dielectric affects capacitance, voltage rating, and behavior under frequency. So we have also the voltage rating here. Every capacitor has a maximum voltage it can handle. Exceeding this voltage can cause breakdown or damage. Leakage current. Over time, small currents can leak through the dielectric, reducing the stored charge. ESR, equivalent series resistance. Real capacitors have some resistance in series with the capacitance, which affects efficiency and behavior at high frequency. So the behavior in circuits, charging and discharging. When connected to a voltage source, the capacitor charges up. The voltage across the capacitor charges over time following an exponential curve. Reactance, that's with AC behavior. We play a lot with the reactance here. Hint, hint, hint. Capacitor resists changes in voltage in AC circuits. They have a reactance that decreases as the frequency increases. Example for traditional applications here. In power supplies, smoothing capacitors reduce voltage ripple after rectification in power adapters. In audio circuits, used to filter low or high frequency for equalizers or crossovers in speakers. In communication circuits, capacitors help tune and stabilize frequency for signal transmission and reception. Limitations in traditional capacitors. We have the dielectric breakdown. High voltages can damage the dielectric, rendering the capacitor non-functional. Limited energy storage. Compared to batteries, regular capacitors store much less energy, but they can release it much faster. This is what we talk about, amps a second or joule. Frequency response. At very high frequencies, internal resistance and inductance reduce capacitor effectiveness. So just basic considerations, traditional information at this point. So moving on now, what is resonance? Resonance occurs when a system oscillates at its natural frequency, amplifying energy due to the alignment of the driving frequency with the system's own frequency. So key conditions for resonance. The reactance, a position to change in currents or voltages of inductive and capacitive components cancel out. Applications of resonance in RF, radio frequency. Resonance is used in circuits like antennas or tuners to amplify or filter frequencies. In traditional transformers, magnetics, resonance in transformers ensures efficient energy transfer, particularly in coupled inductors or tuned magnetic circuits. RF resonance effects. Resonance in RF circuits. In RF systems, resonance occurs in LC inductor capacitor circuits, enabling circuits to select and amplify a specific frequency. Example, in radio receivers, LC circuits resonate at the carrier frequency of the radio station, filtering out other signals. Capacitors and inducers in RF. Capacitors and inducers play a complementary role. The inducers, known as L, reactance increases with frequency. Capacitors, known as C, the reactance decreases with frequency. At resonance, their reactances are equal and opposite, resulting in minimal impedance. This is what we're talking about, folks, when we say at resonance, we can mimic the closest equivalent to superconductivity at that frequency. It's an AC effect. So 3, the near reactive field zone. Very important. Hint, hint, hint. This is the region near an RF antenna or resonator where the electric and magnetic fields are predominantly reactive. Power oscillates back and forth between the capacitor and inducer as reactive power, creating a localized energy storage effect without radiating significant energy. So magnetic resonance effects, so transformers and cores. The resonance of magnetic systems. Magnetic resonance occurs when the inductance of the coil resonates with a capacitance in the circuit. In transformers, this can occur between the winding inductance and any distributed or added capacitance. Core behavior. Ferromagnetic core. Concentrate the magnetic field, enhancing inductances but introducing nonlinear effects, like hysteresis and saturation at high flux densities. Air core inducers avoid saturation, providing linear response even at high frequencies, making them ideal for high frequency applications. Hint, hint, hint. Power transfer efficiency. Resonance and transformers allow maximum energy transfer between primary and secondary windings by minimizing reactance. Basics of resonance condition. Series resonance, voltage resonance. In a series RLC circuit in resonance, the impedance is purely resistive. Voltage across individual reactive components, L or C, can be much larger than the source voltage. And we have parallel resonance, current resonance. In a parallel RLC circuit, resonance minimizes current draw from the source due to high impedance. The inductor, I should say, and capacitors oscillate energy between themselves, reducing the current flow through the resistive part. So, tying it all together, in RF resonance, resonance amplifies or filters RF signals by matching circuit impedance to source impedance. Reactive power dominates in the near field zone, crucial for antenna design and signal transmissions. Hint, hint. In magnetic resonance, transformers ensures efficiency energy transfer by reducing losses in the reactive field. Reactive power oscillates in the windings, but resonance conditions minimize energy loss. Energy storage and oscillation. Capacitors or inductors oscillate energy between the electric and magnetic field, foundational for all resonance phenomena. So moving on to reactive power versus real active power. This is a very important point. So 1, real active power, P, the actual power consumed by the load to perform useful work. Example, lighting a bulb or running a motor. This is measured in watts. Reactive power, Q, power stored temporarily in reactive components, inductors and capacitors, and then returned to the source. This is measured in volts amps. Reactive, so VAR, represents the oscillating energy in the near field zone. Apparent power, S, the total power supplied to the circuit combining real and reactive power. That's measured in volts amps, VA. Power factor, the ratio of the real power to apparent power, indicates how effectively electrical power is converted into useful work. So why reactive power is undesirable in traditional circuits? No useful work, essentially. Since reactive power does not contribute to actual work, it only creates unnecessary current flow, increasing energy losses in transmission lines and components. Wasted capacity. The generation and transmission infrastructures must be sized for the apparent power, S, even though only the real power, P, is useful. Higher reactive power means lower system efficiency. Again, traditional circuits. Increased losses. Reactive power increases the current in the system, which leads to higher resistive losses in transmission lines, transformers, and other components. Voltage regulation problem. Excessive reactive power can cause voltage instability in power systems, leading to undervoltage or overvoltage issues. Mitigating reactive power in traditional systems. Power factor correction. Devices like capacitors or synchronous condensers are used to cancel out the reactive effects of inductive loads. Example, if an inductive load introduces lagging reactive power, a capacitor can supply leading reactive power, neutralizing the effect. Power error correction. Filters. Passive LC filters are often used to eliminate unwanted reactive power in specific frequency ranges. Active power filters can dynamically adjust to varying loads to reduce reactive power. Efficient design. Minimizing inductance in power lines and using high-efficiency transformers help reduce reactive power generation. Traditional systems. Just putting that out there. We're not at the device yet. We're discussing traditional systems so we can have a better understanding of what it is we want to do here. So reactive power in specific scenarios. Inductive loads. Devices like motor, transformers, and coils generate reactive power due to the energy stored in their magnetic fields. These loads require a portion of the current to magnetize the core, which creates reactive power. Capacitive loads. Capacitors store energy in electric fields and create leading reactive power. Though less common in power systems, they can counteract inductive reactive power. Near field zones. Hint, hint, hint. In reactive near field zones close to the antenna or coils, reactive power is significant but does not radiate far or perform real work. In such zone, energy oscillates between the electric and magnetic fields. Why traditional systems ignore reactive power? Measurement standards. Traditional energy meters measures only real power, P, because it's the useful part of the energy consumed. Billing and cost. Utilities charge customers based on real power consumption, while reactive power may incur penalties for industrial users because it strains the grid without providing real benefits. Focus on efficiency. Engineers aim to maximize the power factor to reduce wasted capacity and losses. Reactive power is minimized as much as possible to ensure efficient energy delivery in traditional systems. So in traditional systems, you actually want to kill as much reactive power as you can. Get it all out of the circuit. We don't need it, we don't want it, it's a waste, but that's traditional systems for you. So when reactive power becomes relevant, high-powered systems. In large-scale systems like power grid, reactive power is crucial for maintaining voltage level and ensuring stability. Utilities manage reactive power with capacitor banks, reactors, and static VAR compensators, also known as SVCs. So what this is saying is even the utility company is taking advantage of reactive power for their own usage to stabilize their grid. So, without it, they wouldn't be able to, let's say, carry out miles and miles of energy. But with it, it becomes essentially a local resonator, which is able to transfer the energy efficiently. But just like Joel Mora was saying, looking at the mains, by the time the power really gets to you, is that really a direct source of what's pumping out of the mains power plant? Most likely not. Because if you look at reactive systems, transformers, and resonance, they all become their own energy sinks of inputs. And it's the resonance, the displacement, that actually transfers the energy over. Basically what I'm getting at is it's not an electron transfer kind of system like we all want to visualize because we're all connected to that one wire. We're actually not. And Joel Mora, in his own ways, tried to tell us that. So back to the book here. When reactive power becomes relevant, RF and resonance applications. In RF systems, hint, 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 reactive power is leveraged to create resonant conditions for efficient energy transfer. Example, antenna oscillators, hint, hint, hint. Here it's not undesired, but a functional part of the design. Advanced energy systems. In alternative energy research, harnessing oscillator fields, also known as reactive power, can be explored for novel energy systems. Such approaches challenges traditional power system models. So basically now what we're getting at is what Don Smith tried to tell us. Don Smith was undoubtedly an intriguing character. While some of his information could be considered controversial, borderline misleading, or even irrelevant to the devices in question, he did share some valuable insights. These insights, through cryptic at times, often revealed their simplicity once fully understood. It's important to recognize that Don Smith dedicated much of his life and free time to exploring alternative energy devices. He built and discussed numerous fascinating prototypes, and there is already a wealth of information available about his earlier projects. However, it's worth noting that while we often associate these coil-based devices with Don Smith, similar concepts were being explored by others, such as the Russians with systems like the Capagen, achieving similar results comparable to Smith's. For those interested in these projects, ample resources are available, particularly in Russian language, which can not be easily translated using modern translation tools. Many continue to work on traditional Don Smith setups. Personally, my goal is not to reinvent the wheel or replicate the same system. Years ago, I replicated the Capagen setup using 2 ground loops, achieving a self-looping high-voltage spark gap system that ran successfully for hours. Video of this can be found among my earliest YouTube videos. My focus now is on understanding Don Smith's work in greater depths, how he developed his ideas and where they ultimately led. Notably, little attention has been given to his later devices, such as the so-called soda cooler power supply. This device reportedly provided around 200 watts at 24 volts DC, sufficient to power an AC inverter and run a cooler. What intrigues me the most is Smith's claim that his final design was so advanced and different that it would be unrecognizable compared to his earlier work. Using the notes he left behind, I've pieced together the information, even built a basic prototype. While legal advice has currently prevented me from sharing this device publicly on social media, knowing myself that might change soon. Unlike Smith, I intend to share my findings with this PDF file as a step-by-step, empowering those interested to build it yourself and potentially modify these devices for greater power, understanding the risks involved, of course. So now, building the new Don Smith device. So here's a summary of the parts and materials you'll need for your plasma tube-based high-frequency energy system. The list includes some flexibility to accommodate minor adjustments and testing variations. So I've already took the time to try and calculate a basic something to start with, of course, for anyone to experiment with, and you can basically take it from there. You see? One is the plasma tube. So length about 1 foot. I found some of these on eBay actually. Some of them refer to them as noise generators, but they're plasma tubes. Diameter around 1 inch. The driver, we want a high-frequency plasma driver capable of generating voltages of 5,000 to 40,000 volts, frequency range 10 to 40 kilohertz. This is basically our primary source of chaotic high-frequency electromagnetic fields. And you'll want aluminum foil plate. This is about the length of 12 inches, which matches the plasma tube. Width, this is enough to wrap around the plasma tube with a slight overlap for a typical 1-inch tube diameter. The purpose, this acts as the inner capacitor plate. 3, dielectric layer. Materials, air. Air gap, maintain at least 1 inch between aluminum foil and cone coil. Optional, support dielectric. Teflon, mica, or plastic sheet. This is if you want to do experiments. We're going to skip this part for now. So we get to the cone coil. So essentially, I'm not going to read all of this word per word because it's basically the parts list in great detail. So you can look at that yourself. And it gives you all of the support materials and optional materials for and this assembly checklist. So we're going to skip through all of this and get right to the circuit diagram. So I'm going to pull out the circuit diagram and I'm going to try and go through with it with you here. So as you see from the circuit diagram, we have an isolated power supply, isolated from real ground, very important. And this drives a modern, any high voltage oscillator, high frequency you want. You can build it yourself if you know what you're doing. And here's the connection here. So essentially the no-val piece here is a plasma tube high frequency supercapacitor. And as you can see here, it's a very novel, and just by looking at it, you'll probably say everything is hooked up wrong. But you have to, we're going to get into the detailed workings after. So I'm going to quickly explain the hookup here. So essentially, the high voltage drives the plasma tube on each end, and then we loop it back into through the rectifier into the high voltage ground. So this pulses essentially high frequency DC into the plasma tube. The plasma tube creates all these chaotic and infinite, very high, fast frequencies. So of course, Don Smith talked a lot about filtering, and there was always these calculations, and it was either hit or miss, very complicated, and people seem to always get stuck with the filtering. So here's a very simplified approach to filtering. Let's use the rectifier capacitor as the filtering capacitor instead, a hybrid approach. So essentially, where the rectifier's filtering capacitor goes, one of the plates goes into the foil wrapping around the tube, and the other plate is the open-ended Tesla-like coil that's cone-shaped. Now, all these geometries and configurations are there for a reason, and we will get into that in the explanation. Even the usage of two dissimilar metals for your capacitor here is very important. So again, when you look at the hookup, I've got all the details here of what this does and what you have to do. Tight windings, Tesla-like cone shape, high Q, tight and even windings with high Q emerald coated copper wire. So basically, again, you have a Zener diode that limits your voltage, which can feed an inverter, 24-volt inverter, and run your loads or whatever you want to do with it. So this seems, like I said, if you look at it, this looks nothing like the regular Don Smith. So it's actually very clever. And the thing is, we can say, folks, that this device clearly, if you were to look at it in a sense, because the way this works, it doesn't depend on external fields. It doesn't depend on earth energies. It doesn't depend on heat waves, thermodynamics in the classical sense. It doesn't do any of that stuff like we sometimes want to do with the Bedini device to interact with natural fields, okay? This could work in the cave in the bottom of the earth without any external trigger source, as long as you have your power input, obviously. But what I'm getting at is, if you want to look at it locally, this clearly violates the local rules of thermodynamics, because thermodynamics in mainstream hasn't caught up yet to account for global energy sources. They only account for localized energy sources. So when you're interacting with something like the Dirac sea of energy, traditional electrodynamics doesn't consider that as a global source that you can tap into. If it would, then it wouldn't be a problem. It wouldn't violate the rules. But with that equally said, we have plenty of quantum physics theories and experiments and Nobel Prizes that prove all of this stuff exists. So basically, exactly what Bedini was saying, the quantum physicist doesn't really talk to the electrical engineer much. So they're respectively accepted within their own domains, but no one wants to cross the two together, even though they completely work one and one. So basically what it comes down to is whichever way you want to look at it. If we consider global energy sources in regular thermodynamics, then this does not violate. If you do not want to include global energy sources, then this clearly is in violation of thermodynamics. Because thermodynamics, by definition, you're not able to create order out of a chaos state. So you take all these random energy fields flooshing around and doing chaotic work, one neutralizing the other one out. It's chaotic. You found a system that channels that somehow and creates order and turns that into usable work. By classic definition, you're now breaking the laws of thermodynamics. So very interesting, and it does open a whole philosophical discussion as well. But it's all in which side of the coin you're standing on, really. So with that said, let's explain the internal mechanics, which is very interesting and crucial. What I've explained up to date was basically just the beginning, the summary of what we're at. But you have to understand that for those who have never followed, so where we're trying to get at. So basically it comes down to this: plasma and frequency interactions. Smith highlights the use of plasma tubes operating at 20,000 to 40,000 volts and frequencies of around 20 kilohertz. Here's how this fits into the system and why it matters. Plasma tubes as energy converters. Plasma tubes are essentially gas-filled tubes that become conductive when high voltage is applied, creating a plasma arc. This plasma can interact with electromagnetic fields to convert ambient energy into usable electrical forms. So it can convert ambient, but it's not only that. They serve as nonlinear elements that can enhance resonance and energy transfer within the system. So the key word here is nonlinear element. Hint, hint, hint. Resonance enhancement. Operating the plasma tube at its natural frequency or a harmonic allows the device to amplify energy inputs through resonance. Plasma has unique dielectric properties, enabling it to interact with high frequency oscillations more efficiently than solid-state materials. High voltage and frequency. Voltage 20,000 to 40,000 volts. High voltages increase the energy density within the system, allowing the plasma to sustain intense electromagnetic interactions. Frequency, let's say 20K. High frequencies improve the efficiency of energy transfer in the system, as many environmental energy sources, ambient RF or Schumann resonance, operate in similar ranges as well, and its harmonics of. Electromagnetic field interactions. Plasma can act as a medium for scalar waves, hint hint, or other unconventional waveforms that Smith and others theorize can tap into ambient or vacuum energy field. The difference is Don Smith never gives you the whole breakdown theory on how that actually gets done. I do here, and it's going to be in the follow-up. So again, you're welcome for that. The interaction of the plasma with Tesla coil emissions create a high energy environment that enhances energy extraction. The role of the plasma tube. The plasma tube acts as a nonlinear high-frequency energy converter that interacts with the high-voltage, high-frequency outputs from the driver circuit. Here's why this is notable. Nonlinear medium for energy interaction. Plasma is highly conductive and exhibits unique nonlinear electrical properties. When exposed to high-frequency oscillations, it can amplify certain energy effects, such as resonance. It interacts with the electromagnetic field to produce oscillations that can interact with ambient energy sources, such as the Earth's potential or electromagnetic fields nearby, even already being generated by your trigger, which is the most important part here. Enhanced resonance effects. By placing the plasma tube in the path of the high-voltage, high-frequency output, it likely serves as a resonant element that magnifies the oscillating energy. The magnification could lead to greater energy extraction from the environment if resonance aligns with ambient electromagnetic fields. That's optional if you want to do that. Don't need to do that. Just putting it out there. Ionized pathways for energy flow. The plasma tube creates ionized channels, hint hint, that facilitate high-efficiency energy transfer. These pathways might act as conduits for tapping into additional energy, potentially from the vacuum energy or atmospheric fields. Waveform transformation. Plasma tubes can introduce harmonics and other nonlinear effects into the system, potentially enabling energy harvesting across a wider frequency spectrum. This could increase the total energy available downstream. So, how these concepts work together in Don Smith's device. High frequency, high voltage generator as the driver generates high frequency, high voltage AC. The plasma tube converts this AC into a dynamic interaction with surrounding fields, exploiting resonance to extract energy. So the simplified inverter design converts the high-frequency oscillator into usable DC or quasi-AC power ready for practical loads. Using a 25-volt Zener diode for regulation. Voltage stabilization. The Zener diode is connected in parallel across the output terminals, positive to cathode, negative to anode. When the voltage exceeds 24 volts, the Zener diode conducts in reverse, shunting the excess current to ground and clamping the output voltage at 24 volts. Feeding the 24-volt inverter. The regulated 24 volts DC can now safely supply the inverter, which converts DC into 60 Hz AC for practical applications. So what happens to the extra energy? The system converts any excess energy into high current at low voltage, which manifests in two key ways. Shunted by the Zener diode, the Zener diode dissipates the excess voltage as heat. While this protects the downstream components, it is not efficient for energy recovery. In other words, if you don't use the load, it's not the best way because it wastes it as heat. In larger systems, the heat dissipation might require cooling mechanisms drawn into the load. The high current capacity of the system becomes available to the inverter and the load in practical terms. If the load requires high current, example 24-volt motor, the system can supply it efficiently. For devices requiring less current, the system runs under capacity and the excess is either not used or dissipated. Potential energy utilization strategies. To better understand the surplus energy, consider the following approaches. Split the output. Use a voltage divider or additional regulation circuitry to create multiple voltage level. Example, 24 volts for the inverter and another high current low voltage load for other loads. Energy recycling. Implement a charge storage system, example supercapacitors or a secondary battery bank to capture surplus energy. This stored energy can either power additional devices or be reinjected into the system when needed. Secondary use for high current. The high current low voltage output could be used directly for heating elements, resistive heaters, electroplating or electrostasis applications which requires high current. Adjustable load integration. Add adjustable resistive or inductive loads to dynamically consume the excess energy without wasting it as heat. So why no transformer losses in this design? This system achieves high current at low voltage without transformer-like VI linear losses because it uses capacitive and inductive components rather than magnetic induction for energy regulation and conversion. Very important, hint, hint. In transformers, linear loss, voltage and current scale inversely, with losses proportional to resistance and core inefficiencies. Power loss is higher due to resistive heating, R losses in the windings, and hysteresis eddy currents in the core. In Don-Smith's system, the voltage step down and current boost are achieved through capacitive and resonant effects that minimize linear resistive losses. The energy transformation process emphasizes resonance, where energy is efficiently transferred without the typical losses seen in transformers. This is why Don Smith's design maintains high efficiency despite high current output. The load determines the energy flow. Full load or high power demand. If the load, example inverter, requires substantial power, the system supplies it directly as 24 volts DC at high current. Minimal energy reaches the Zener diode because the load consumes most of the system's input. The Zener operates passively on only kicking in during voltage spikes or minor fluctuations. No load or low power demand. While the load draws little or no current, the Zener diode activates to clamp the voltage and dissipates the surplus energy as heat. In this situation, efficiently draws because energy cannot have been used for work is wasted. So the key characteristics of the system, voltage regulation with Zener diode. The Zener diode clamps the voltage at 24 volts, ensuring the inverter or load always receives a stable input. Excess energy is either consumed by the load or dissipated as heat through the Zener. High current output. The system can deliver high currents, hundreds of amps at 24 volts, ideal for demanding tools like inverters, motors, or resistive devices. Resonance efficiency. The system avoids conventional transformers' inefficiencies by leveraging resonance and capacitive effects for energy transformation. So here's the simplified analogy. Imagine you're using a water wheel. Conventional systems, the energy output is limited to the flow of water you directly supply. Smith's approach, he claims to find a hidden water source, example underground springs or rainwater, that adds to the wheel's power, making it appear that the wheel is generating more energy than you're putting in. In summary, Don Smith's over-unity claims relies on tapping into an external energy sources, ambient fields or zero-point energy, exploiting resonance to amplify energy, using asymmetric regauging to create energy flow imbalances. While the principles are theoretically interesting, replication requires advanced understandings of resonance, grounding, and energy harvesting techniques. So this is why I say you must read the book before you try to experiment with this. So concept of using capacitive plates around the plasma tube. Energy capture mechanism. Concepts of using capacitive plates around the plasma tube. Energy capture mechanism. The plasma tube produces a range of high-frequency signal harmonics and nonlinear effects. Placing capacitive plates or cylindrical capacitors around the plasma tube can capture these oscillations as displacement currents, adding to the overall energy output. Why low capacitance can work. High-frequency spikes from the plasma tube provides rapid charging and discharging, which can compensate for small physical capacitance by maintaining a quasi-steady flow of energy, a kind of HF supercapacitor. The rectifier and Zener diode can stabilize these bursts, ensuring a relatively consistent 24-volt DC output. Advantage of dynamic energy filling. The high-frequency pulses, fast spikes fill the gaps between the slow discharges. Harmonic utilization. Multiple frequency components add layers of energy capture. The core idea, wrapping the filter capacitor around the plasma tube. Energy-rich environment. The plasma tube creates a high-energy field full of nonlinear oscillations, high-frequency harmonics, and electromagnetic bursts. Wrapping the rectifier's filter capacitor around the plasma tube allows the capacitor to interact directly with this dynamic field, improving its performance and reducing the need for a large capacitor. High-frequency advantage. At high frequencies, even the small capacitance, like 20 pF, can behave effectively due to the reduced impedance. This low impedance means the capacitor can still effectively smooth high-frequency components of the rectified signal despite its small value. Passive energy utilization. By integrating the capacitor into a high-energy plasma field, you're passively tapping into its harmonics and bursts to improve capacitor charging and smoothing performance without active feedback. How this exploits additional energy. Asymmetric regauging in action. In conventional circuits, energy flows symmetrically with input and output balance within the system's boundaries. By embedding the rectifier's capacitor within the plasma tube's electromagnetic field, you create an open system. Hint, 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 very important, where external energy from the plasma's dynamic field can influence the circuit. This field enhancement acts similarly to asymmetric regauging, where the potential energy differences across the capacitor is influenced not just by the rectified output, but also by the plasma tube's field. Capacitor's multi-role. Energy smoothing. The capacitor fulfills its primary role of filtering the rectified DC. Energy absorption. Simultaneously, it absorbs and integrates high-frequency harmonics, burst, and ambient energy from the plasma tube's dynamic field, adding energy to the system. Dynamic charging from environmental interaction. The plasma tube acts as a nonlinear element, interacting with both the circuit and the surrounding environment. The interaction may create conditions where ambient energy sources, atmospheric potential, zero-point energy, which is where we're most interested in, or even ground currents are drawn into the system. The capacitor positioned directly in the field effectively collects this energy during its charging cycle. Why this fits in Don Smith's concepts. Nonlinear exploitation. Don's devices often relied on nonlinear interactions where conventional circuits rules don't fully apply. Placing the capacitor in the plasma tube's field aligns with this principle. Open system dynamics, very important. By introducing the capacitor to the plasma's environment, the circuit may behave as an open system that interacts with external energy fields, bypassing the closed system limitations of traditional electrodynamics. Energy amplification without extra input. The capacitor's ability to gather high-frequency bursts passively aligns with Don's claim of energy amplification from external sources. Example, ambient fields are zero-point energy. Self-inductance and enhancing capacitance. The secondary winding, which is very important here, Tesla-like coil has intrinsic self-inductance due to its elliptical geometry. This inductance interacts with the system's high-frequency oscillations, effectively amplifying energy transfer between the capacitor plates. The coil's resonance interacts with the plasma tube's field, potentially aligning with harmonics or creating standing waves that amplify local energy density. Nonlinear and asymmetrical interactions. The asymmetry between the aluminum foil and coil introduces nonlinear energy flows. The helical geometry captures more high-frequency bursts from the plasma tube. Asymmetry may allow the system to couple more strongly to external energy fields, zero-point or atmospheric potential. Dynamic energy storage. The Tesla-like secondary coil can store energy momentarily as magnetic fields, which are then discharged back into the system during gaps in capacitor charging. Advantages of this design. Very high efficiency. The Tesla coil-like secondary acts as both a capacitive plate and an inductor, reducing the need for separate components. Asymmetric energy couplings. The non-symmetric capacitor enhances interaction with the plasma tube's field, potentially drawing energy from external sources. Compact and multifunctional. Combines filtering, energy storage, and amplification in a single structure. Very efficient. Dynamic amplification. The self-inductance and resonance of the coil work synergistically with the capacitor to amplify energy bursts. Very interesting feature of this device, why tuning isn't necessary in this setup. Plasma tubes broadband emission. Plasma tubes emit an extraordinary range of frequencies and harmonics due to their nonlinear nature. These include fundamental driving frequency from the power supply, harmonics and subharmonics from ionized gas dynamics, random noise and bursts caused by chaotic electron interactions. This means the plasma tube is constantly producing energy across a vast frequency spectrum. High Q coil finds its resonance passively. A high Q coil is highly selective and resonates strongly at its natural frequency or frequencies near it. The plasma tube's Broadband energy ensures that at least some frequencies align with the coil's resonant modes, causing it to resonate passively and contribute energy efficiently into the system. Dynamic and independent triggering. The coil doesn't need active tuning because the plasma tube essentially pings it with all possible frequencies. When the coil resonates, it naturally amplifies energy at those frequencies, contributing to the circuit's overall dynamics. Key benefits of this approach. Simplified design. You don't need precise calculations or tuning of coil lengths or turn. The plasma tube's Broadband spectrum handles that. Self-adaptive behavior. The coil adapts to whatever frequency excites it most strongly, allowing it to contribute passively to the system without requiring intervention. Harvesting unknown couplings. The chaotic and nonlinear emissions of the plasma tube may tap into external or unknown fields, ambient electromagnetic energy or zero-point energy. The coil's high Q ensures it captures and amplifies these couplings efficiently. How it contributes independently. Capacitance and inductance interplay. The coil acts both as a capacitor plate, interacting with the coil and with the foil and plasma field, an inductor storing magnetic energy and contributing resonance effect. This dual role ensures it is constantly engaged in energy dynamics. Energy amplification at resonance. When the coil resonates at certain plasma tube frequencies, it amplifies energy at those points, effectively boosting the overall system output. Noise contribution. Instead of being wasted, random noise from the plasma tube is converted into usable energy by the coil's resonance. System dynamics without strict tuning. Broadband driving force. Plasma tube provides endless energy bursts across multiple frequencies. High Q coil passively responds to the frequencies most aligned with its natural modes. Energy integration. The capacitor coil structure collects, filters, and amplifies the plasma tube's chaotic energy for smoother DC output. By integrating the inductive coil as part of the capacitor plate, the capacitor now serves three functions simultaneously. 1. The filter. The capacitor smooths the pulsating DC from the rectifier, acting as a traditional filter. Resonator. The inductive coil, Tesla-like secondary, resonates with a high frequency and harmonic components from the plasma tube, dynamically enhancing energy capture and distribution within the system. Dynamic dielectric recharging. The resonant behavior contributes to continuously filling the dielectric gaps during the capacitor's charge-discharge cycles, maintaining a more stable quasi-DC output. How this works in detail. Capacitor as a filter. The capacitor is directly across the rectifier's output, filtering the high voltage, high frequency pulsations. Its small capacitance, 20 to 50 pF, is compensated by the high frequency bursts from the plasma tube, the additional smoothing effects of the inductive coil plate. Inductive coil as a resonator. Resonance with high frequency noise. The inductive coil resonates naturally with certain frequencies from the plasma tube's Broadband emissions, amplifying them passively. These amplified resonant frequencies create a higher energy density within the capacitor. Dynamic energy storage. The coil stores energy in its magnetic field during its resonance cycles and contributes it back into the capacitor when the field collapses. Enhanced dielectric charge maintenance. Filling the holes. The resonant energy from the inductive coils ensure the air dielectric within the capacitor remains more consistently charged, compensating for the inherent instability of using a small capacitance. Quasi-DC output.
By dynamically reinforcing the charge in the dielectric, the capacitor maintains a smoother and more stable output voltage, even with a highly fluctuating input from the rectifier. Benefits of this approach: triple functionality. The capacitor acts as a filter, a resonator, and an enhanced charge maintaining, reducing the need for all these additional components and losses. Stable output without active control. The high Q resonance dynamically stabilizes the capacitor's charge without requiring precise tuning or external feedback. Efficient energy utilization. Resonance ensures that even chaotic or random frequencies from the plasma tube contribute usefully to the output. Smaller capacitor size. The combined inductance and resonance makes it possible to use a much smaller capacitance while maintaining effective smoothing. So expected behavior: quasi-stable DC output, improved energy capture, and dynamic energy storage. Why this dual metal? This is very important. Don Smith found this out in his own ways, but didn't have a very clear explanation, that you have to use a dual metal plate configuration, different metals. It's almost like what we do with the PEG quantum power cells with two dissimilar metals. It seems like when you have two dissimilar metals, when you introduce high energetic fields to it, there's a similar action that happens where the electrostatic fields are enhanced when you have two different metals of different mega electron volt value. And Don Smith figured this out without getting into the great details, but did say in his own ways that this is part of his capacitors, and it's very important for that your capacitor setup needs to have two different, it's almost like building a electromagnetic version of a PEG cell, you see. It seems like two different metals don't necessarily need an electrolyte in between to interact with each other at the quantum scale. The mega electron volt value doesn't need a ion conductivity is what I'm getting at. If you give it very interesting materials like the PEG is one, or different field variants, it will, what I'm getting at, there's more than one condition to trigger these potential differences between two plates. And in the earlier work of Don Smith, he did the ion valve, which does the same thing. If you use like two different metals from the ionization, you end up having like what almost looks like a galvanic effect. So, but it's an electrostatic version of it instead, is what I'm getting at. The pure quantum mega electron volt value of two different elements. If you have a compatible medium in between, such as an electric field, it's one field interacting with another field now, and you're making that link. So that enhances the interaction. So my own ways to try and explain that, because there's no clear explanation to why you need to use two different metals for an air capacitor, but I'm explaining it to you now based on my own observations and little hints that Don Smith left us. So now back to what I was saying here, why this dual metal plate configuration works and why it is very important. Diverse metal properties. Aluminum foil plate. Aluminum acts as a non-ferromagnetic and highly conductive, making it excellent for creating a uniform electric field in a capacitor. Its non-magnetic nature minimizes interaction with the plasma tube's magnetic dynamics, focusing its role on charge storage and field creation. Magnetic copper wire plate. Copper wire, though not ferromagnetic, serves as a dynamic capacitor plate with self-inductive properties due to its helical winding. The core's geometry and material allows it to interact with magnetic and electromagnetic fields more actively, contributing to resonance and energy amplifications. Dynamic asymmetry. The stack difference in material properties between the aluminum and copper coil introduces asymmetry, which is key to enabling nonlinear energy interactions. This asymmetry creates a broader range of energy couplings, electric, magnetic, and high frequency, with the plasma tube and its emissions. Alignment with Don Smith's concept. Don Smith often emphasized the importance of combining static and dynamic energy behaviors in his systems. Hint, hint, hint. Aluminum serves as a static energy storage plate, while the copper coil acts as a dynamic resonant element, enhancing the system's interaction with ambient energy. So how it acts like a supercapacitor at high frequency. High frequency behavior of the capacitor. The small capacitance of the aluminum plate and copper coil capacitor becomes highly affected at high frequencies due to the reduced impedance. Even a small capacitance, 20 pF, provides low impedance at high frequencies, allowing significant current flow. High frequency energy from the plasma tube keeps the capacitor charged and replenishes energy gaps dynamically. Dynamic resonance effects. The copper's coil's inductance introduces resonance which amplifies energy at specific harmonic frequencies of the plasma globe. This amplifies the charging and discharging of the capacitor, further enhancing its energy throughout. Energy recycling in the dielectric. The dielectric of the capacitor stores and discharges energy rapidly, simulating the behavior of a supercapacitor at high frequencies. This constant charge-discharge cycle ensures a steady energy flow into the rectifier output. High current at the Zener output. The Zener diode clamps the voltage to a fixed value, example 24 volts, while the capacitor coil system ensures a high current, low voltage output by maintaining a quasi-stable DC level. The high-frequency pulses are effectively smoothed by the capacitor-coil combination, feeding continuous current into the load. Key factors for high current, low voltage output. High charge-discharge rate. The capacitor resonating with the plasma tube's high-frequency energy rapid charges and discharging, maintaining a consistent flow of current. Zener voltage clamping. The Zener diode ensures the voltage never exceeds the regulated level, 24 volts, making the output stable and usable for low voltage, high current loads. Efficient filtering. The coil's inductance acts as a secondary filter, further smoothing the pulsating DC from the rectifier and contributing to a stable output. Dynamic energy flow. The asymmetry between the aluminum plate and copper coil introduces nonlinear energy dynamics, which can amplify current flow into the output stage, similar to the ion valve or even the PEG 3350 cell. What to expect at the Zener output? Stable low voltage, high current, and continuous energy flow. Practical considerations. Current limit of the Zener diode. Choose a Zener diode with a sufficient power rating to handle the expected current. For example, for 24 volts at 10 amp, the Zener must dissipate 240 watts. A series of high-power Zeners or active regulations might be needed for large currents, assuming you're not using them in your load, right? Capacitor coil optimization. Ensure the coil has a high Q factor to maximize energy transfer and resonance effects. This just means in English a tight windly, even coil with a lot of windings, making it high Q reactive. Rectifier current rating. Use diodes with sufficient current and voltage ratings to handle the amplified energy flow. Load matching. The output's high current capability makes it ideal for driving low voltage, high current devices like motors, LEDs, or battery chargers. Summary of behavior. Supercapacitor-like dynamics. At high frequencies, the capacitor coil system dynamically stores and discharges energy, mimicking a supercapacitor. High current, low voltage output. The Zener diode regulates the voltage while the capacitor coil system supports a steady high current flow to the load. Stable output with plasma tube as driver. The plasma tube's chaotic high-frequency emissions are smoothed and stabilized, resulting in a quasi-continuous DC output. And this is very important here. The coil shape is not just a Tesla-like secondary. It's a Tesla-like secondary that's shaped out like a cone. It starts narrow in the bottom and builds up. And I have the dimensions for this. Very important. So effects of the cone-shaped high Q coil. Enhanced broadband response. The cone shape introduces a natural gradient in inductance and capacitance along the length of the coil. The wider top windings have higher inductance and lower self-capacitance, while the tighter bottom windings have lower inductance and higher self-capacitance. This gradient creates a broader range of natural resonant frequencies, effectively making the coil more responsive across a wider bandwidth. Improved coupling to external fields. The wide top acts like a broad collection area, improving the coupling to ambient electromagnetic fields. This is particularly useful for harvesting energy from diverse frequency sources, as the geometry inherently captures more harmonics and noise. Gradient resonance. Different sections of the core resonate at slightly different frequencies due to the variation in winding, spacing, and geometry. This allows the coil to self-adapt to a wider spectrum of input signals, making it especially useful in chaotic or noisy electromagnetic environments. Example near a plasma tube. Higher Q at selective points. The coil retains its very good high Q properties at specific resonant frequencies with a broader bandwidth, enhancing its ability to interact with multiple energy sources or signals at once, and not just one or two nearby its point, but a whole wide array of them. Magnetic and electric field interactions. Magnetic field concentration. The cone shape naturally concentrates magnetic flux at the narrow end of the cone, the bottom. This can amplify localized magnetic effects and improve couplings to nearby circuits or components. The electric field spread. The white top disperses the electric field over a large area, improving energy collection and interaction with external signals. The field gradient effects. The varying geometry creates a field gradient which can enhance interactions with nonlinear or chaotic energy systems, such as those from a plasma tube or spark gap. Applications and benefits. Broadband resonance application. Ideal for systems that require energy harvesting, interaction across a range of frequencies. Works well in high-frequency environments, including plasma tubes, RF application, or electromagnetic noise capture. Perfect! Energy amplification. The cone shape's inherent asymmetry may align with asymmetrical regauging principles, potentially amplifying energy interactions. Compact and efficient design. Compared to uniform cylindrical coils, cone-shaped coils can achieve broader responses with fewer turns, making them lighter and more compact. Challenges and considerations. Construction complexity. Winding a cone-shaped coil requires precision to maintain uniform spacing, very important, and alignment. Ensuring proper insulation and mechanical stability might be more difficult than typical cylindrical coils. So how to build the cone-shaped coils. So I'm going to skip this part because it's pretty well, yeah, just a step. So now go into nonlinear capacitive effects. Using air as the dielectric with the cone-shaped coil introduces nonlinear capacitance, as capacitance vary dynamically. This is what Tom Biernan was saying. You guys need to build nonlinear capacitors. This is it. This is it right here. Distance changes. Any variation in spacing between the aluminum foil and the cone coil caused by vibration, thermal expansion, or field interaction changes D, leading to dynamic capacitance shifts. Exactly what Tom Biernan says you need to have. Field strength. The plasma tube produces a highly dynamic electric field, creating nonlinear charge distribution across the plates. Frequency-dependent behavior. The cone's coil varying inductance along its length adds a frequency-dependent component to the capacitance, creating effects like those Tom Biernan discusses in terms of frequency-varying nonlinear capacitance. Exactly what I was saying. Tom Biernan kept hinting at this kind of a capacitor. Here it is. High-frequency stability. At high frequencies, 10 to 40 K from the plasma tube, effective capacitance. The small physical capacitance behaves more effectively because the impedance of the capacitor decreases with frequency. While this value may generally seem high, it's suitable for capturing and storing high-frequency energy bursts. Dynamic resonance. The cone's coil inductance contributes to resonance effects, amplifying energy transfer at certain frequencies. Field enhancement. Air as the dielectric reduces energy loss and allows the plasma tube's chaotic fields to interact directly with the plates, maximizing energy capture. So here is how to design some potential coil capacitor dimensions. So I'm going to skip that, but the information is all there, and the calculations and the diameters. I want to get into the theory here. So I'm just going to skip all of this. And So, okay, by using this cone coil capacitor as both the filter capacitor for the rectifier and as the dynamic energy interaction element, you can achieve quasi-stable DC output, dynamic energy filling, and high current at low voltage. How it all works together. The cone coil capacitor is placed directly across the rectifier's DC output terminals. It smooths the pulsating DC by rapidly charging and discharging at high frequencies. Plasma tube interaction. The plasma tube's electromagnetic fields interact with the capacitor dynamically, refilling energy gaps in the dielectric, compensating for small physical capacitance. Zener voltage regulation. The Zener diode clamps the output voltage to 24 volts, ensuring a stable, usable DC level. Load drive. The combination of the capacitor's dynamic smoothing and the Zener diode's regulation allow for the system to provide high current at 24 volts, ideal for powering low voltage, high current devices. Key advantages: dual functionality, efficient energy utilization, high current capacity, and stable output. So there's the implementation steps, a bit of a review here. I'm going to pass that. So again, a good point here. Why the coil naturally filters? Inductive reactance. The inductive of the coil introduces a natural impedance to high frequency components. Higher frequencies, example noise spikes, face greater impedance and are attenuated. Lower frequencies of steady DC are allowed to pass through with minimal resistance. Field interaction enhanced filtering. The coil's inductive properties interact with the dynamic fields from the plasma tube, further suppressing unwanted harmonics and creating a more stable signal out of that energy. Resonance benefits. If the coil resonates at specific frequencies of the plasma tube, it selectively amplifies energy contribution at those frequencies while filtering out non-resonant noise. Why this is ideal for your system: compact and efficient, dynamic response, quasi-DC stability. And let's see here. Summary. The coil side of the capacitor acts as an inductive filter, enhancing signal stability while serving its primary role in energy storage and resonance. This dual functionality is a major advantage, simplifying the circuit while improving performance. By interacting dynamically with the plasma tube's chaotic field, the coil-capacitor combination delivers efficient filtering and energy reinforcement. So Don Smith, again, told us that, oh, this taps into the vacuum energy, but never gives us any details. So I'll give you the details. On Bearden's Dirac-C analogy, the Dirac-C constant. In quantum theory, the Dirac-C is a theoretical construct where the vacuum is seen as a sea of virtual particles, such as virtual photons and electron-positron pairs. These virtual particles exist in an energetic equilibrium, and disturbances like resonance can cause them to transition from virtual states to real observable particles of energy. Resonance and virtual energy conversion. Bearden suggests that under resonant conditions, specific perturbations, example high-frequency electromagnetic fields, can shake the Dirac-C, forcing vertical particles or photons to manifest as real energy. This process creates localized holes in the virtual particle C, which the vacuum then energetically fills by delivering real energy. How this concept aligns: dielectric holes and resonance. In this cone capacitor design, the dielectric holes refer to depleted energy states in the dielectric material caused by rapid charge-discharge cycles. Localized field imbalances created by the plasma tube chaotic high-frequency energy and the capacitor's interaction with it. Resonance, especially from the cone coil geometry, could amplify these effects, creating a dynamic system where the dielectric absorbs energy rapidly, displacing it into the surrounding system. The vacuum, in turn, refills these depleted states, the holes, by contributing energy through quantum effects. Virtual photon conversion, popping energy out of the dielectric. The high-frequency, high-energy oscillations in the capacitors interact with the dielectric field at a quantum level. This interaction might cause virtual photons or energy states in the dielectric to pop out and manifest as real usable energy. Vacuum refilling mechanisms. As these energy bursts deplete the dielectric, the vacuum wants to restore equilibrium by delivering energy, real photons, or field energy into the system. This is akin to Bearden's idea of tapping into the vacuum's zero-point energy reservoir. Resonance as the key driver. Shaking the Dirac-C. Resonance amplifies electromagnetic interactions in the dielectric, shaking the Dirac-C and enhancing the transmission of virtual energy to real energy. Field dielectric coupling. The plasma tube's chaotic fields combined with the cone's coils' resonant effects create nonlinear oscillations in the capacitor that maximizes this energy conversion process. Continuous refilling. As energy is extracted from the dielectric or the vacuum via the dielectric, the system dynamically refills those energy gaps through ongoing interaction with the external fields. Practical implications: enhanced energy output. The capacitor system operating under resonance could theoretically amplify output power by exploiting these vacuum interactions. Self-reinforcing dynamics. The process of creating and refilling holes in the dielectric creates a feedback loop. The more energy extracted, the more the vacuum contributes to refill the dielectric, potentially exceeding the apparent input energy. Nonlinear capacitive effects. These vacuums interaction could explain why the capacitor's behavior under resonance is nonlinear, with energy bursts appearing to exceed what classical physics predict. So I have a comparison here to Tom Bearden's theories and this concept. And the conclusion basically is this concept of filling the holes in the dielectric is very much in line with Bearden's direct C vacuum interaction theories. The combination of high-frequency resonance, nonlinear capacitive behavior, and dynamic energy exchange with the vacuum field creates a system where energy could be amplified beyond classical expectations. This offers a fascinating experimental pathway to explore resonance-driven vacuum energy extraction. So, there you have it, folks. I know it's a lot. I skipped through a few parts, but again, please review this a few times, and if you understand, you'll be able to build any kind of these devices. And I hope, again, if you do, please, as I said before, please don't try and make a star of yourself, because you're only going to ask for trouble. Don't try and make money with this. Don't try and be, cool at the coffee shop to make everyone else feel dumb. But use it, if you do succeed, your family, your friends in need. Use it to help people. And of course, within our own groups and people interested, sure, show them how it works. But if it's just for ego, to make money, to social following, self-glorification, especially when you're messing around with commercial quality power, folks, that never ends well for you. We're not quite there yet. But if folks, if hobbyists, and let's say, my friends and my family start building these, and then your friends and families, let's say by the time we end up having 10% of the general population that just goes screw it, and they're all running on their own energy systems, it won't be very long before the mainstream society is going to have to wake up and say, yeah, we know they're doing it, it's accepted, but we haven't updated our main models. So we should do that and go with the flow and just catch up. So this one here won't be so, you see what I'm getting at? When it's big tech that tells you it's time to switch, then it's okay to brag about it and show it off to the whole world. But until big tech tells you to do that, it's a bad idea to just do things that are potentially very bad to you. So that's just my advice. And with that said, folks, this pretty well explains it. I don't know what else I can possibly contribute, what I can say. Just, I guess, follow your heart by this point.